Announcement number one. We have this cookout tonight over at C4C. Okay. I'm not exactly sure where it is, but last year
the problem was always that the entire background, so that's an even minus s thing that can be compensated for it by the e to the plus s with a sufficiently fine question.
You need some kind of photo ID.
I think, yeah.
Okay, they'll have beer there.
Yeah.
The university is
I mean,
completely
there are some
neurotic
people
about alcohol.
like Giddings who thought even perturbative corrections were going to solve the problem. I mean, so
number
there were some people who said it, but I think that was really tilting. It was yeah. Okay. All right. Anyway, I just wanted.
I was going to organize a hike last weekend, but I got wiped out.
Beautiful.
If you ever get involved in organizing tasks, my advice to all you young people is do not let it happen.
That's basically the first time.
Don't do it. Okay. But I'll do something this weekend. I'll put some maps over here on the table. Probably when we break for lunch and you can take a look at it. But the idea basically is if you want to go up in the woods, I'll be over in the big parking lot by Kittredge around 8:45 or so on Sunday morning. And what I want to do is do a loop on the north side of Green Mountain. If you think you're tough, I can tell you arbitrarily difficult places to go. I have been there, but I don't want to do them on Sunday. Okay. If you want something simple, I can tell you simple places to go up there too, which are just as pleasant as where the tough guys are going. They're probably just nicer. Okay, that's it. Okay, we introduced Mr. DeWolf, who will introduce.
Unless anyone else wants to be in the middle of that chain, I could introduce you. So we're happy to have Nima with his second lecture on effective field theory.
All right. First, sorry for screwing up the timing this morning. I somehow got in my head I was talking at 10:45. So thanks to Tom. You see, it isn't just late time that causes me problems. It's early times as well. Okay. So taking off from our example of a little toy model of modeling a rope with balls and springs, remember what we're after is there's some physical system, we're making a model for it, and then the model has a few parameters and we have to match the parameters of that model with some experiment. And once we match the parameters of that model, we'll make the same predictions for the long distance behavior of the rope as anyone else who chose their own choice of cutoff and balls and springs. And maybe someone else wants to have balls of different mass and two different kinds of spring. None of those things will matter if in the end everyone matches the same tension and mu. And so you can make any picture. So the intuitive idea is you can make any picture you like for the ultraviolet, and so long as you match some correct long distance physics, then again to accuracy, to power law accuracy, p squared divided by cutoff squared, you're going to get the same answer. And so to begin with, let's review how this works in the kind of more standard language of seeing how cutoff dependence disappears when you do calculations and you rewrite bare parameters in terms of physical parameters. These are all things that you've definitely seen, but let's imagine we're talking about, again, our phi to the 4 theory. So I'm going to be even sloppy about signs here, okay, and mostly we're going to care about the quartic coupling. I won't care so much about the mass squared. So I'm going to look at a 4-point function. And so here's the answer at one loop plus the other two channels. Okay, and so this is lambda minus lambda naught squared over 32 pi squared, what I wrote down yesterday. Integral 0 to 1 dx log of the cutoff squared divided by m naught squared plus x 1 minus x, let me call it p1 plus p2 squared, plus the other channels. All right, and notice that here I'm working in Euclidean space. We'll come back, as I promised, we'll talk more about Lorentzian things later, even a little bit today. But all the momenta here are Euclidean. There's a plus sign here. All these p squareds are positive. Okay, and so what we want to do as our friends with the balls and springs is we want to determine the parameters of this model in terms of some physical observable. So I'm just going to define, again, this is all very familiar to you, but I'm just going to define lambda star to be the value of this 4-point function at some particular point in momentum space, p star. All right? So my model has just two parameters, lambda naught and m naught, but I'm making a prediction for a continuous infinity of things, right? The value of all the Green's functions at all the momenta, so I have a lot of things I can choose to try to determine these parameters. A very convenient thing to do is to just choose the value of the 4-point function somewhere in momentum space. And so now I'm going to solve for lambda naught in terms of lambda star. And clearly, there's a perturbative expansion for it. So I'm going to write lambda naught is lambda star plus some a lambda star squared plus dot dot dot. And to determine this, determine what this coefficient has to be in order to match lambda naught. So this is, again, this is exactly the same as saying that k in my balls and springs model is t over delta x, right? I'm just trying to determine the model parameters from a physical observable. And so it's obvious, in this case, just perturbatively, what a is going to be. A is just going to be exactly that expression in the integral sign with the p there replaced by p star. Okay, so a will end up being this integral 0 to 1 dx log cutoff squared over m squared plus x1 minus x p1 plus p2 star squared plus the other channels. And so finally, when I express G4 in terms of now lambda naught that I've determined in terms of lambda star, then I get an expression where the cutoffs disappeared. Okay, I get lambda star minus lambda star squared over 32 pi squared log now m squared plus x1 minus x p star squared over m squared plus x1 minus x p squared. This is p1, 2 plus the other channels. Okay, so that's the standard thing that you've seen many times in your field theory courses, that when you express the observable quantities of Green's functions in terms of other observable quantities, of course all the divergences go away, right? That's the, and so indeed, the cutoff has disappeared here entirely, and I've expressed this observable now that depends continuously on all these p's in terms of its value as observed at one particular p star. Okay, and if I'm a little, if I write that integral a little loosely, then I'm also seeing that all the cutoffs are gone. But there's another interesting thing, that G4 at p is lambda star plus 3 lambda star squared over 16 pi squared log p over p star plus dot dot dot. Okay, so and so we have this interesting phenomenon, but maybe lambda star small. I mean, I literally measure, this 4-point function at some value of the momenta, maybe at 10 GeV or something. I measure it, and now I can predict what this is everywhere else. I can predict what it is at 100 GeV. Great. At 100 GeV, I use this formula, and I get this correction, and let's say lambda is a 10th. Okay, this is fine. Great. No problem. But let's say, lambda is a 10th, but I want to go all the way up to p near the gut scale. Then that logarithm becomes a big number. The log, just practically, the log between the string scale, the Planck scale, and the weak scale is around 30. Okay, so the log is a big number. The alphas in the real world, the coupling constants, are around a 30th. So the quantity alpha log is of order 1. All right, and so now if you look at this, you're like, oh shoot, if p is close to p star, I'm in pretty good shape. But just a practical thing. I've measured it here, right? And I want to predict what it is super far away. Well, shit, I guess I have to do a 2-loop calculation, 3-loop calculation. Big trouble, right? A lot of work. So the cutoffs are gone. All of that is fine. But we do see there's a logarithmic variation, just locally. There's a little logarithmic variation of what we would think of as this sort of effective 4-point function as we move in momentum. All right, so we're going to say something about that in a moment, of course. As I said yesterday, that's the entire heart of effective field theory, and the renormalization group is dealing with these logs. Okay, but there's a separate question that we can ask, which is again analogous to the question we asked in our toy model. Is it possible to change the coupling constant, the bare coupling constant with the cutoff to keep the physics fixed? Right, again, if you come up with one cutoff, I come up with another cutoff, we'll have different bare couplings, but we'll keep the physics fixed. So it's a natural question, how do I change the bare couplings with cutoff to keep the physics fixed? And in this case, well, we can easily work it out. Things depend on lambda naught. So we take the formula for G4, and I just ask, how does lambda naught have to vary with capital lambda in order for the physics to be fixed? And the only interesting thing here is what happens when lambda d d lambda hits that log, right? When lambda d d lambda, capital lambda d d lambda hits a log, I get 1. And so just from that formula, you see that I have to have lambda d d lambda is equal to 3 over 16 pi squared lambda naught squared of lambda. And so I can do it. If I make that choice, I can do it, and the physics is independent of scale. Now, I want to emphasize what's magical about this formula. What's magical is the following. I mean, I could always say, I could just always demand that the observable is independent of the cutoff and get a formula of this sort. Lambda dd naught of lambda is equal to some beta that depends on lambda naught and lambda. That would be tautological. If I handed you a completely random function, right, you could just define what I mean by the running lambda naught of lambda by just taking the derivative and demanding that it's 0. This is tautological and empty. Okay? This is a tautology. What's interesting, instead, what's not a tautology, and what we call the Wilsonian beta function in quantum field theory, is that this object only depends on the coupling at lambda, and it has no explicit lambda dependence at all. It has no explicit dependence on the cutoff. Okay, this is an interesting statement. So no lambda here, no cutoff here, and this is the Wilsonian renormalization group equation. So the fact that you can change the bare parameters with the cutoff in a cutoff independent way, okay, in order to keep the physics fixed is non-trivial, and that's the Wilsonian RG. Now, this may seem very intuitive, and obvious. Sorry. And before we do that, let's just say some familiar things. For example, at this order, I can solve this equation, and I already discover interesting things. I discover that lambda naught at some lambda is lambda naught at some original cutoff, capital lambda naught, over 1 minus So from this equation, for instance, we see the famous Landau pole. That says that if you take this theory with some cutoff, and now you try to raise the cutoff, higher and higher and higher, at some point, this lambda naught of lambda will blow up at very, very high energies. So that already tells you something interesting, that whatever the heck this cutoff regulated theory is, it cannot make sense all by itself up to arbitrarily high energies. As you attempt to make it sense up to arbitrarily high energies, at some point it will break down, if you hold the low energy physics fixed. So if you demand that, at the scale of 10 GeV, I have some 4-point interaction for the scalars, then if I attempt to model this by my cutoff system of a phi to the 4th theory, that will break down somewhere, exponentially far away, but it will break down somewhere. The only way not to have it break down is for the 4-point function to be 0. So that's why people often say this backwards, that phi 4 theory is trivial. But anyway, it's not. Either way, we learned something interesting from actually solving these Wilsonian RGs. But anyway, we're not going to focus on that too much. What I want to talk about now is why did this happen? I mean, we see sort of mechanically that it happened. By the way, this is, of course, very close to the proof of renormalizability, right? This is the fact that it's possible to absorb all of the logarithmic dependence on the cutoff in a redefinition of what we mean by the bare parameter, something we just took for granted from our balls and springs model because it was so obvious. And now we did a one-loop calculation in the slightly fancier context of field theory, and we see that it's possible. But so that the fact that it's possible is essentially the proof of renormalizability, right? But why did it happen? It seems so intuitive and obvious, but I want to point out that it has real teeth. If you think it's very intuitive and obvious, you should go tell Mr. B, P, H, and Z not to have wasted so much time in the 1950s. Because, in fact, it makes a rather dramatic claim about the structure of Feynman diagrams. Okay, so in order to see what the claim is, so this thing has teeth. And so let's go back and write G, any G we like, it could be G4, as a series. So it's lambda naught. Instead of writing the log again and again, I'm going to define T to be log lambda over P. Okay, so let's say we're doing the same calculation, G4 at P. But imagine that we're very powerful and we just did the calculation to all orders in perturbation theory. So the formula looks something like lambda naught, and then there's some lambda naught squared A1T. That's just what we saw, right? At one loop, something like lambda 1 squared. And then at two loops, we'd have lambda naught cubed. And then in principle, there could be something that goes like T squared. You just think about two-loop diagrams. There are two loops. Each one of them could have a logarithmic divergence. You're not going to get a log cubed at two loops. There's only two loops, right? The biggest log you could get is log squared. So you could have a T squared, but maybe there's something sitting underneath it, which I'll call B2T. And then I'm very powerful. I go to three loops. So there's some A3 T cubed plus B3 T squared plus C3T, and so on. So this is the diagrammatic expansion, or imagine we did these computations. Now, this intuitive statement that there should be a Wilsonian RG, that there should be some way to change the parameters with cutoff to keep the physics fixed, well, let's see what it predicts for us here. So, we want lambda dd lambda of G4 to be 0 as a consequence of some equation of the form lambda dd lambda of the coupling is equal to just alpha lambda naught squared plus beta lambda naught cubed plus gamma lambda naught to the fourth plus dot dot. And again, the crucial thing is that there's no capital lambda dependence in this equation, right? So I'm just writing down an equation that says how the coupling varies given what the coupling is. Okay, so let's just do it. Let's take that formula and let's just look at the cutoff, dd cutoff of it. So from the top term, I'm just going to get alpha lambda naught squared. So 0 has to equal alpha lambda naught squared plus beta lambda naught cubed, gamma lambda naught fourth when it hits this guy. And now let's first go through everyone else and let the cutoff dd cutoff hit the t's. Okay, so cutoff dd cutoff is just d by dt. Okay, so from the other things I'm going to get, for example, from the first term I'll get lambda naught squared a1. From the second term I'll get lambda naught cubed. And I've stopped at order lambda naught to the fourth, so I'm not going to go past order lambda naught to the fourth in anything I do. From the second term I get 2a2t plus b2. From the third term I get 3a3t squared plus 2b3t plus C3. And I'm going to stop there because I hit lambda naught to the fourth. Then let me go and look at the ones where the derivative hits these lambda squareds out in front. Okay, so I'm going to have plus, from the second term there, some 2 lambda naught times alpha lambda naught squared plus beta lambda naught cubed. I'm going to stop here because I've ordered lambda naught to the fourth already. Okay, times a1t. And then from the second term, I'm going to get 3 lambda naught squared times alpha lambda naught squared. And I'm going to stop here because I've already ordered lambda naught to the fourth, multiplied by a2t squared plus b2t. Okay, so 0 has to equal all of these guys. And now let's just match the various coefficients, term by term. Okay, so at order lambda naught squared, if I just look at the coefficient of lambda naught squared, there's an alpha and there's a plus a1. So this is alpha plus a1. And so we have to have that alpha plus a1 is 0. Good. That just tells me what alpha is. Alpha is equal to negative a1. We just saw that, right, from our computation. So you do a one-loop calculation. One-loop calculation gives you a1, and that tells you what the alpha is in the RG. So far, so good. Nothing non-trivial seems to be happening. That's just what we did and saw at one loop. So let's go to the next term. This is an expansion in both lambda and t. So let's look at the term that looks like lambda naught cubed t. So this is already slightly more interesting because we have one piece that looks like 2a2. But then from the bottom, we have something, from the first term of the bottom line, we have something that looks like 2 alpha a1. So plus 2 alpha a1. So this has to equal 0. All right, well, that's interesting because this is no longer a formula for alpha. We know what alpha is. Okay? So for this to be true, it actually tells us what a2 is. It tells us that a2 has to equal a1 squared. Right? Well, that's not non-trivial. In order for this to be true, the 2-loop answer has got to be determined entirely from the 1-loop answer. That's amazing. We didn't have to touch any calculation, a 2-loop calculation, but somehow it has to be true that the 2-loop coefficient is given by the computation that we did already. Okay, let's keep on going. So what about the lambda naught cubed piece? Lambda naught cubed tells us, well, we have a beta from the first term, and we have a b2 from the third term, so we get that beta plus b2 is equal to 0. Good, so that tells us beta equals minus b2. Okay, so again, if I want to know what the next term is in the renormalization group, in the Wilsonian renormalization group equation, I have to do a 2-loop calculation and extract not the leading log that goes like t squared, but the subleading log, the first piece that has a log in it that shows up at 2 loops. That gives me the 2-loop coefficient. Very good. But now let's keep on going again. If I look at order lambda naught to the fourth t squared, then I learn that 3a3 plus 3 alpha a2 is equal to 0. Okay, just comparing terms. And this tells me this pattern keeps on going, that the 3-loop coefficient has got to be given in terms of a2, which is given in terms of a1. So we learn that a3 has got to equal a1 cubed. And if I look at lambda naught to the fourth t, from here I get that 2b3 plus 2 beta a1 is equal to 0. And so that tells me a constraint as well. It tells me that b3 has got to equal a1 b2. Right? And so on. Okay. Finally, the constant piece here, lambda naught to the fourth t, just tells me, I won't write it down, it just tells me that gamma is equal to negative C3. Okay. Sorry? Oh, sorry. Thank you. I'm not. Okay. Okay. So you see the point here, right? Is that when you think in terms of Feynman diagrams, these are all separate diagrams, right? And yet, this seemingly very intuitive and simple fact that it should be possible to change the couplings with the scale to keep the physics fixed only works if the answer you get from Feynman diagrams has this sort of remarkable structure that should really be organized a different way than we wrote it down. I mean, even just the way to write it down really looks more like this. Really, we should write G4 is lambda naught plus. And then there's something that looks like A1 lambda naught squared T plus A2 lambda naught cubed T squared plus A3 lambda naught to the fourth So these are what you would call the leading logs. And then there's the first subleading log. So B2 lambda naught cubed T plus B3 and so on. Okay, it's more naturally organized in terms of the leading logs, the subleading logs, the sub-subleading logs, and so on. The point being that this coefficient that you determine from a one-loop calculation determines all the rest of them. This coefficient that you determine from a two-loop calculation, all the rest of them. This coefficient that you determine from a three-loop calculation determines all the rest of them, and so on. Okay, is this clear? And this is why the proof of renormalizability is not a trivial statement. Okay? Graphically, it's not a trivial statement. You have to sort of prove that the Feynman, graphically, you have to prove that this is in fact how the divergences, the ultraviolet divergences in the Feynman diagrams organize themselves. Now, as I said repeatedly, this is what BP, H, and Z and various people did in the 1950s. And the real difficulty with this business has to do with the famous overlapping divergences that start at two loops. So part of the reason why in your field theory courses you kind of get the sense there's nothing particularly interesting going on, and okay, you just cancel divergences and it's not a big deal, is that all the juice starts happening at two loops, which you don't see. Okay? So that's really where things start getting interesting. This exponentiation of the logs, the fact that the higher leading logs are determined by the lower ones, is something that's only interesting and you start seeing at two loops. Now, this old literature, as I stressed yesterday, was kind of horrible and seemed kind of complicated and graphical and combinatorial. But here there's a suggestion for the reason why why there's something missing, because these logs are being generated, as I stressed yesterday, by an integral that receives equal contributions from all scales. So the reason this is difficult in the standard way of organizing perturbation theory graph by graph is that we're thinking about physics graph by graph rather than scale by scale. And if we think about it scale by scale, if we see these logs generated gradually somehow, if we reorganize our thinking about perturbation theory so that we can see these logs arise gradually rather than just in one shot and summing over them graph by graph, that's going to give us a better chance of understanding what is going on. Having said all of that, and I toyed with lecturing on this subject here, but I thought it would end up being a little too off the beaten path from what people here are interested in, although I find it fascinating myself. Starting in the 1990s, people like Alan Kahn and Dirk Kreimer and others went back to this old horrible seeming BPHD way of proving renormalizability, and they actually found there's a beautiful mathematical structure associated with it. There's a beautiful Hopf algebra structure associated with that old graphical proof of renormalizability, and phrased in this Hopf algebraic way, it's much more transparent. Okay? And you can, I mean, that's why I toyed lecturing on that subject. It's actually pretty easy to explain. So I used to have the physicist chauvinist pig attitude that Wilson solved all these problems for us and we don't have to think about it anymore. But these other guys came and said, no, that old way of thinking about things was not terrible. you can actually associate with this very nice top algebra structure. And in fact, this new way tells you more things that Wilson is blind to. Okay, for instance, there's some interesting number theoretic content to the beta function coefficients in quantum field theory. In fact, there's very interesting number theoretic content in correlation functions and amplitudes in quantum field theory, period. But even in something as simple as beta function coefficients, if you look at QED and you look at the QED beta function, you find that 1 loop, 2 loops, and 3 loops, the coefficients are rational numbers. Okay? But starting at 4 loops, there's a zeta of 3 that makes an appearance. So some interesting transcendental numbers make an appearance. Zeta values and multi-zeta values start making appearances in beta functions. So if you're a Wilsonian, as we'll review, you don't give a rat's ass what these numbers are. You just know they are what they are. You have to do some calculations to get them, and that's it. But this other way of organizing your thinking, this Hopf algebraic way of organizing your thinking, actually makes a prediction for where you see what kind of zeta values, at what loop order, why, and so on. So it has some more insight into the number theoretic content of these quantum field theoretic quantities. And those structures are very reminiscent of the kind of mathematical structures we've seen in the context of scattering amplitudes in the last 10 or 15 years. So I think there's something, to me, fascinating going on to try to connect this very deeply Euclidean picture about the renormalization group as understood in this somewhat more abstract Hopf algebraic way, and the sort of dynamical Lorentzian questions we've been thinking about in the context of amplitudes. Anyway, that's just a side comment. This BPHD stuff is not totally crap, and I encourage you to try to read some of these Kahn-Kreimer papers. Some of them are quite readable. Okay, so but anyway, we're going to stick with the Wilson, and so that's what we're now going to explain. Why does this happen? By the way, even without being any more precise about it, it's clear that the fact that all these higher order logs are slaves to the lower one is also giving us a lot of hope that the problem we ran into, that even when we got rid of the cutoff, the answer grew logarithmically. So if I try to go from p at a GV to p at the gut scale, I have that big log. Do I have to worry? I have to do some brand new 2-loop calculations, 3-loop calculations? Probably not, right? Because somehow the leading logs are slaves to the sub-leading ones. Okay, so that's going to help us understand how to resum those logs, how to deal with those logs as well. So that's what we're now going to do. We're going to understand where all this comes from the Wilsonian point of view, and also give a precise connection between this Wilsonian way of thinking and the normal renormalized perturbation theory. Okay, any questions about this? So this is all probably very familiar to you, but I just want to stress where the magic is. There is some magic. This is not just all dimensional analysis, blah, blah. It was all obvious and guaranteed ahead of time. There is something slightly magical going on. Okay, so now we're going to get to sort of effective field theory at last, proper. And of course, whenever you do effective field theory over and over again, you talk about the notion of integrating something out. Okay, we're going to integrate out heavy fields, heavy modes, and so on. So let's first just talk about that in the most trivial setting. So let's say you have a theory of 2 scalar fields, phi and chi. Phi is massless, chi is massive. Okay, so maybe phi has its own phi to the 4 interaction, but also there's a chi. Chi is massive, and there's an interaction that looks like g phi cubed chi. All right. So let's say that's the theory of the world. And you're an experimenter, and M is very big. M is very big, much bigger than the energy of your machines. You don't know that it's there. So you're only looking at, this is now it's a Euclidean question again, but you imagine that you're only measuring correlation functions for this light field. So let's say I have some phi, phi, phi. I'm only interested in things that look like this. All right, now since there are only phi's appearing here, I might as well do the path integral over chi. And in this particular case, very exceptionally, this is not a generic thing at all, of course. In this particular case, you can actually do the path integral over chi exactly. Why can we do it exactly? Because in chi, it's just Gaussian, right? If there's a linear term here, the phi cubed here looks like a source. Otherwise, everything is Gaussian. So that's why this is the most trivial case. But if we do it, we're left with something else. Just a path integral over d phi. Still, these phi's are sitting there, times some minus some s effective of phi, where s effective of phi is just, well, the things that were sitting there already, plus some kappa phi to the 4. But I have a new interaction that looks like lambda squared, phi cubed, 1 over a box plus m squared, phi cubed. Phi is like the source, right? So I have some correction that looks like that. And once again, so long as I'm at distances that are large compared to 1 over m, energies that are low, or the p squared involved is small compared to m, it's useful to do a Taylor expansion of that propagator.
Is it a chi phi squared or chi phi cubed?
This is a phi cubed. I just wanted to make it, I don't know, I'll call this lambda. Okay. Okay, so this is, of course, if I expand this out, this is lambda squared phi to the 6th over m squared plus lambda squared phi cubed box phi cubed over m to the 4th plus dot dot dot. So already I get an infinite number of higher dimension operators having integrated out chi. And diagrammatically, this is just that there's this process that involves a chi on the inside, phi's on the outside, but a chi on the inside that I need to reproduce in this theory that only has the action phi, right? And so everything that I get from that diagram has got to be included as some vertices in my effective Lagrangian. Okay, so this is the most trivial, the most standard version of integrating something out. You're literally integrating it out in the path integral. Poof, right? You just integrate over the guy, and you induce, already in this simple example, an infinite tower of higher dimension operators. And as we said yesterday, these higher dimension operators are the way the long distance theory knows there was something going on at very high energies. Okay, so if the low energy person was lazy and was just measuring sort of very easily measurable things, they would just notice kappa. But if they worked very hard and measured 3 to 3 scattering, they might notice, gosh, there's a 3 to 3 scattering there, and it's very small, but its presence is telling me something about the existence of something at some much higher energy scales, right? And the details of what those higher dimension operators look like reflect in some way the details of whatever the ultraviolet theory is. Of course, I can't literally trust that formula when the boxes become comparable to m squared, right? This expansion is bad. The expansion has literally a finite radius of convergence, right? There's a pole that's sitting there at p squared equals minus m squared, okay? So I literally cannot trust this up to very high energies, which of course makes both perfect Euclidean sense and even more perfect Lorentzian sense, which because now I can't ignore the fact there was this particle there that I have made, right? But so long as I can't make the particle, then all of its effects are usefully encoded in these higher dimension operators. Okay, so now, just that's the sort of simplest version of integrating out. But with this in mind, let's go back to our problem. Let's go back to try to understand phi-4 theory and so on. And so let's even say that you started off, let's even tentatively say that you started off with the Lagrangian that you wanted, d phi squared plus m naught squared phi squared plus lambda naught phi to the 4. Okay, and I didn't even put anything in. Okay, but now imagine that I'm doing the path integral. Now I'm going to imagine that I've just switched to doing even this path integral in momentum space. I'm certainly free to do that. In other words, I'm looking at correlation functions directly of phi's in momentum space. So no problem with that. E to the minus s of phi. and lambda. But here I'm imagining that this path integral over d phi is only on modes that have some p magnitude of p less than a cutoff lambda. Okay, so this is the way in which we're regulating things, right? We're putting a cutoff. Now, if you read Polchinski's paper, there's some little technical discussion about how precisely to define this. You don't want to put a really sharp cutoff because you don't want to introduce a scale that's sharper than the scales on the problem. These are all kind of irrelevant technicalities. All right, so let's just focus on the things that really matter here. So we're being a little loose about what we mean by this. Okay, but you see. I'm only interested in this correlation function when these momenta are way smaller than capital lambda, okay, at very low energy. So that means that I can do this path integral in steps. So again, normal perturbation theory is to do the path integral all at once in perturbation theory by perturbing around the Gaussian solution. And Wilson's idea is simply to reorganize the calculation. So Wilson says, what if I first do the path integral over all the modes where p is between some cutoff capital lambda and some new lower cutoff capital lambda prime. So here's the old cutoff lambda. Here's a new cutoff capital lambda prime. I'm still interested in p's that are down here, that are smaller than all of them. Okay? So what I'll do is just do this path integral now, first with the piece where all the p's are less than lambda prime. The phi's are sitting there because they're all less than lambda prime. But then I'm left with the path integral with the p's between lambda and lambda prime, e to the minus s of phi and lambda. And I'm just going to define this whole sucker to be e to the minus s of phi and lambda at the new cutoff lambda prime. Okay? So you see it's conceptually exactly the same as integrating out a particle, a massive field, except I'm not actually integrating out a field. I'm integrating out the very high frequency, very short wavelength modes of the field phi itself. And from this point of view, you see that it's kind of silly to begin with to force the Lagrangian to only have the terms that look like m squared, phi squared, and lambda naught phi to the 4, because the second I integrated something out, between lambda and a half lambda, then clearly I'm going to induce, just like we saw in our example there, clearly I'm going to induce all the higher dimension operators that are sitting there anyway. Of course, they'll all be sitting there suppressed by the scale capital lambda. That's not a big deal, right? But there's no particular reason to stick with this very simple form to begin with. So let's not. Okay? And in fact, in the real world, there's absolutely no reason to expect that's what in the real world, we don't even expect the real world to quantum field theory at arbitrarily short distances because of quantum gravity. But even way before we get there, at any point in time, there's some physics that we haven't seen. There's absolutely no reason to expect that the actual effective Lagrangian only has the dimensionless couplings or the renormalizable couplings. Okay, so from the get-go, we're going to imagine that we have a more general action. So in fact, let me just go back. And even if you like, you can put some coefficient even for the kinetic term. This is a little bit conventional whether you do it or not. But we're going to imagine that we have all of these couplings. So let me call this lambda 4. Sorry, I'm going to now switch notation slightly. I'll call them H4 and some H6, phi to the 6, and all the other terms that we can possibly have. Okay? And we're going to divide couplings, but we're going to divide the couplings in this effective action into the familiar sets, into the things that we call relevant, marginal, and irrelevant, which, since we're doing perturbation theory here, are really just determined by the engineering dimensions of the coupling. So relevant are the things that have positive engineering mass dimension. So these are the couplings whose dimensionless size grows as you go to lower and lower energies. Marginal are the things that have are dimensionless engineering dimensions, and irrelevant, which have negative engineering mass dimensions, and are the things that are naively unimportant at very long distances. Now, I'm not going to keep dividing relevant and marginal. I'll just call all of these guys by little r to remind us that they're relevant in the colloquial sense. They're the ones that we care about. Okay? And these are going to be irrelevant. Okay. Now, as we said yesterday, most naively, you would say that you're kind of in the soup with figuring out how to do physics with this effective action because it has infinitely many coupling constants, right? Less naively, you would say, no, come on. It's the other way around. All these things are irrelevant. We even call them the name irrelevant. They're totally unimportant at very low energies, and we only care about them if you do very, very precise experiments. Then maybe you care about one or two of them, right? But the vast majority of them, infinitely many of them, are totally irrelevant at low energies. And the difficulty that we talked about, one of a few difficulties, is like that statement is not literally true because of quantum corrections. So it's not literally true because of the diagram that we drew yesterday. Like I might want to say that this H6 is irrelevant. And certainly it seems irrelevant compared to this at low energies. That's what we said yesterday. So this is H6, whereas this is H4 squared over P squared. Okay? So at low energies, this is going to dominate over that for sure. So that's the sense in which the irrelevant guys are tiny. However, if I take this diagram and I close a loop, then certainly naively, there is an H6 cutoff squared from doing that loop integral that corrects H4. So there's a correction to H4 that goes like H6 times cutoff squared. H6 itself might be some dimensionless coupling lambda 6 divided by cutoff squared, but then I see that I can't ignore lambda 6 because there's a correction to lambda 4 that goes like lambda 6. It's just being a little loose here. So that's one of the reasons why you can't just throw it out. Okay? You might want to throw it out, but you can't just throw it out. All right, so let's see. So now let's explain, following Wilson and Polchinski, what is going on. But before diving into the proofs, which are extremely simple, really once you have the idea that you're organizing, you're thinking about perturbation theory scale by scale, everything else kind of is like falling out of bed. It's just that Wilson, anyway. So we'll see how simple it is. But what I want to first do is tell you what the correct statements are, and then just spend some time with the correct statements. Just see how they imply various things that you know, and then we'll prove the statements. Okay, so here are the claims. So there are two related claims. One is that whatever your Green's functions are, which you've chosen, in principle, we have relevant and irrelevant couplings, that these Green's functions are actually the same as the Green's functions for a different theory. You change the theory a little bit, where the relevant couplings might change, but the irrelevant couplings are set to 0 with the same cutoff. Okay? So you have one cutoff. You naively think you have infinitely many coupling constants. However, in this infinite family of theories, they're all going to give you the same predictions at low energies. So long as if you want to get the predictions from one and the other, you just have to slightly change what you mean by the relevant coupling. Sorry, of course, up to corrections of order p squared over cutoff squared that we're going to declare that we don't care about. Okay? So that's the first claim. The second claim is very closely related to the first one as well, is that now in the set of theories where we set all the irrelevant guys to 0, it's possible to choose g of p and just lambda relevant with lambda irrelevant to 0 and lambda, that these guys can be made to depend on lambda with a Wilsonian beta function such that these Green's functions are lambda independent, again, up to things that are suppressed by powers of p squared over lambda squared. Okay, so just to say, these are extremely simple things, but just to say them again, the first statement is about one model, one coupling, one cutoff, one model, but it's telling you that the predictions that you get from this model, despite the apparent infinitely many different couplings, that in fact the predictions of this model are very well parametrized by very few couplings, namely just the relevant couplings, right? And that any two of them, this theory gives you exactly the same predictions as another theory where you ignore all of those guys. All you have to do though is correctly change. You can't keep, that's the phenomenon we saw. I can't just throw them out. But we also saw here what the cure was. Okay, I can't throw it out. I just redefined what it meant by lambda 4. I don't know what lambda 4 is anyway. It's one of my parameters, right? I'm going to end up matching these things by comparing with experiment at low energies anyway. But it's a claim about a relation at a fixed cutoff between this entire family of theories. The second claim is having parametrized them in this intelligent way. Now it makes sense to ask the question how things vary as you lower the cutoff or you change the cutoff. And there is a nice renormalization group equation that tells you how the bare couplings change with the cutoff to keep the physics fixed. I want to stress that this Wilsonian, often when people talk about beta functions, we'll just talk about this in a moment, but often when people talk about beta functions, you sometimes get the sense that the beta function, maybe it makes sense at one loop and two loops, but beyond two loops, maybe you hear words like it's scheme dependent. How many people have heard things like that, right? It's a little confusing seeming, okay? And we'll talk about schemes in a moment. Every time in physics, this is not just here, every time in physics something seems like arbitrary and ill-defined, it's because human beings got involved, okay? So it's some human thing, and the physics itself does not have these features at all. In particular, when you're making a choice of a model, this is my model, I've committed. I have a cutoff, lambda, this is how I'm doing it, this is my regulated theory. Zillions of ways of doing it. You put a momentum cutoff, do dim reg. If you want to regulate Yang-Mills theory, many of you are CFT lovers and string theory lovers. One way to regulate Yang-Mills theory is to stick it in n equals 4 super Yang-Mills. It's this beautiful finite theory and just give a mass to all the particles, other than the gluons, of course, right? So there's zillions of ways of regulating something, but pick any one of them in that way of regulating the theory. The Wilsonian RG is locked. It's a completely God-given thing. It's a fact about the ability to change the parameters of your model with the cutoff, what you mean by the cutoff to keep the physics fixed. So the Wilsonian RG is a totally God-given thing. Okay, so now we're going to prove these statements soon, but I want to spend a few minutes and just talk about them. How am I doing for time, Oliver?
You have 22 minutes.
22 minutes. You're fascinatingly precise. All right. So claim 1 is the kind of intuitive claim about effective field theory period, right? Claim 1, remember, we could have gotten these higher dimension operators. We get them by just scaling, coming down from one scale to the other. They could just be sitting there already because we integrated out some heavy particle, like we saw in our first example, right? Claim 1 is what tells us that we can do physics at low energies without knowing the theory of everything. Okay? Claim 1 is what tells us that all the details of high energy physics are absorbable into a finite number of parameters that matter at low energies. And of course, almost everything that we know in the real world, so this is the This is the number one reason why there's only a few coupling constants that determine everything we know about the world around us in the standard model, right? We don't have to, it might seem amazing that you can understand all the interactions of electrons and photons just by concatenating over and over again this little elementary 3-point interaction between 2 electrons and a photon. Or are we just lucky? Why couldn't there be some fundamental 17-photon 2-electron interaction? And then we have to concatenate that, okay? And that would naively make life much, much more difficult. And the point is, even if that guy is there, by this dimensional analysis reason, it has a scale associated with it. And if you go to large enough scales compared to that, it just doesn't matter at low energy. So the fact that the world is understandable at low enough energies in terms of a finite number of parameters is not luck, nor is it a rule of nature, which is what people used to think when they said that renormalizability is forced on us because otherwise we can't compute. It's just a feature of the fact that in the real world, for rather mysterious reasons, these reasons are known as the cosmological constant and the hierarchy problems, but anyway, for rather mysterious reasons, there's a very large separation of scales between microphysics that's associated with quantum gravity and the Planck scale and so on, and the scales of you and me and even atoms, molecules, quarks and leptons and so on. Okay? But when there is such a separation, then it's guaranteed that physics at low enough energies is described by a finite number of parameters. Now, in the real world, we have one example of an interaction who's the most important example of an interaction that's dominantly irrelevant, and it's gravity. Right? Gravity is given by 4 dimensions, given by dimensionful coupling constant. Every amplitude involving gravity goes like energy squared over m Planck squared. And so gravity is really technically irrelevant in this sense. We care about it only for the famous reason that it happens to add up coherently at very large distances, despite the fact that it's extremely small. So the flip side to the fact that we don't need to know the theory of everything to do physics at low energies, there's no free lunch. The flip side is that it's very difficult to discover the theory of everything from low energies. Okay? So if you want to know something about what's going on at super duper short distances, super high energies, you have very little access to it from physics at very long distances. Just like it's very difficult to tell something about what the complicated distribution of some collection of charges from looking at it very far distances. The most you can do is 2 things. One, you can do these much more difficult experiments where you look for tiny effects. So all these effects that we're ignoring here of order p squared over cutoff squared, you can just kind of go look for them. Right? And so to do that, you have to work very hard and make very precise experiments. So when you hear people say that we know that the electron doesn't have any substructure up to 10 TeV from experiments that were done at LEP by the late 1990s, that's because people looked very precisely at electron-electron scattering, and they looked for the presence of higher dimension operators involving electrons, and they didn't see any. Okay? And by doing incredibly accurate measurements, if you're doing experiments very roughly at 100 GeV, if you can measure something to an accuracy of 1 part in 10,000, then you can rule something out, some higher dimension operator, some effect that goes like energy squared over cutoff squared. The energy is 100 GeV. Accuracy is 10 to the minus 4. You can say that cutoff has got to be bigger than 10 TeV or so. All right? So that's one way you can go about doing things, a very difficult way to do very precise measurements. Another way you could look for, a much better way to look for the effect of higher dimension operators is to look for some process where for some accidental reason what you get from the leading order dimensionless interactions in the low energy theory has a symmetry. Okay? So for example, in the world of QED with just electrons and muons, you imagine just QED with electrons and muons, and there's nothing that can change electron number into muon number, or vice versa. Electron number and muon number are separately conserved. But it's an amazing fact that if you take a muon, which is this teeny tiny elementary particle, and give it 10 to the minus 6 seconds, it decays. That's an ginormous lifetime. 10 to the minus 6 seconds on the time scale of elementary particles is a ginormous lifetime. Even more ginormous is a neutron that sits there in empty space for 15 minutes before it decays to a proton, electron, and empty electron neutrino, right? So there are these clearly tiny effects that violate muon number but conserve the muon plus electron number. and the tiny effect that violates individual neutron and proton number, but keeps the sum intact, right? So that meant that in the effective theory, in the first example of just QED, there was a higher dimension operator. In fact, there's a 4 fermion operator, and this is how people managed to know that it exists. This is how Fermi managed to know that the Fermi scale, which is around 100 GeV, exists in the year 1933, before they had accelerators that were even going to the few hundred MeV scale, right? Because there was a symmetry of the low energy theory that was, an accidental symmetry of the low energy theory that was violated by a higher dimension operator. So that's how the weak interactions were discovered, and that's what we do today when we look for proton decay, okay? Or we look for neutrino masses, or another example of something that violates one of the approximate symmetries of the standard model, okay? All right, so anyway, so that's the strategy to look for these things, but at 0th order it's hard. And so it's the flip side of the fact that we can do physics at low energies without knowing the theory of everything, is it's difficult to discover the theory of everything from low energies. Okay, so much for claim 1. Claim 2 is the traditional statement about renormalizability, okay? And what I'd actually now like to do is more precisely connect claim 2 to what we normally call renormalized perturbation theory. There's really extremely little content in what I'm saying. It's just language. But this is to sort of dispel any picture you might have that this Wilsonian stuff and the usual way of doing things and, Peskin and Schroeder or whatever are somehow, while maybe philosophically the same, technically they're not quite the same. No, they're just exactly on the nose the same. Okay. All right, so remember, what is it that we're trying to do? What we wanted to do is to see, we wanted to write a formula for the bare coupling in terms of some lambda star, right? And the way we did it before was to define lambda star to be some Green function at a particular place, P star, right? That's just a particularly convenient way of doing it, but just very, very slightly more generally, all we want to do is find a formula. We want to be able to express the relevant couplings at the scale lambda in terms of some other couplings that we'll call physical couplings. Lambda phys plus A lambda phys squared. Right? We want to find some formula of this sort. And of course, A is going to depend on lambda. The lambda physics don't depend on lambda. A might depend on lambda. Okay? Okay? We want to do this such that the Green's functions that are really functions of lambda, this is my model, but when I express the bare couplings in terms of these ones, so this is going to turn into G of P, and this is going to be some function of lambda phys, that this is lambda independent, cutoff independent, again, up to P squared over cutoff squared. Okay? That's the traditional statement of renormalizability, right? That you can, when we say you can absorb all the divergences into redefinition of the bare parameters. All right. Now, there's an extremely simple way of doing this. That's given to us by the Wilsonian renormalization group. Sorry, before I say that, this is where some arbitrariness comes in. So when you take this formula, there's choices in how you do this. There's some B of lambda physical cubed plus ... right? Here's where we make a choice. Any particular way of writing this in order for this to be true, any particular way of doing this is called a scheme. Okay, so this is what we call a scheme. And it's a totally human choice. You can see that it's a human choice because if you make one and it works, I can make another one. I'm going to say my lambda phys is your lambda phys plus B prime lambda phys squared plus C prime lambda phys cubed. You see, we can go back and forth between definitions of what I mean by lambda phys between different people. Okay? Just they can be perturbatively related to each other and they'll all work. There's no, so this, what's non-trivial is that it's possible to do this at all, right? But the particular way in which you do it has nothing invariant about it. Okay, so this is a scheme as opposed to a regulator. Again, the regulator is you've committed to a model of the world, right? The once you regulate, you've decided the calculations that you're doing. Okay, here there's nothing invariant. But there's something that I like to call the Wilsonian scheme, which is especially natural. And here's what we're going to do. I'm going to take the Wilsonian RG, but I'm going to evolve it backwards. So I'm going to start at some low scale mu. I'm going to choose some lambda phys at mu. The scale mu is arbitrary. Okay, so I'm going to also call lambda phys at mu. And then starting with this boundary condition, I'm going to evolve the RG back, the Wilsonian RG back, until I get something up here. Okay, so up here I'm going to get some lambda naught at lambda. Which is now going to be some function of lambda phys at mu, well, and it depends on lambda in some way, right? But you see, by construction, it's guaranteed that once I do this, the answers are independent of the cutoff lambda, right? So simply because if I go to a different lambda, then I know if I run the Wilsonian RG, so I start with lambda, I go to some lower lambda prime. The point of the Wilsonian RG is that I'm getting exactly the same physics. But this prescription is guaranteeing that that's where I'm going to end up when I go down to the lower lambda prime, simply by running the RG backwards. Okay? So this is just a way of guaranteeing that using the Wilsonian RG, that I can find this relationship between the bare parameters and some parameters that I'm giving a name, lambda phys at mu, okay, such that the physics is independent of the cutoff lambda. Is that clear? Okay, so this is, and this is a scheme. This is a scheme in which the beta function, to all orders, there's no, oh, I can't trust it at g cubed, 2 loops, blah, blah. No, in this scheme, the beta function is the Wilsonian beta function. Okay? But now the beta function for this physical, in this scheme, if I ask for this question, what is mu dd mu, lambda phys of mu, it's the same Wilsonian beta function of now lambda phys. So notice we've done a little, it's all extremely simple, but we've done a little move here, right? We started with this question, how do I change the bare parameters with the cutoff to keep the physics fixed? Now we're parametrizing my model in a different way. We're parametrizing my model in terms of mu and lambda phys. Okay? By doing that in this particular way, we've removed all reference to the cutoff. But the way lambda phys has to change with mu is exactly the same Wilsonian beta function that we got from the structure of the model from seeing what happens as we change the cutoff. Okay? Okay. Now, of course, in this picture, we've removed all the real distinction between the bare couplings and the physical couplings. You see in this picture, there's one thing. There's couplings that change with scale. Lambda phys at mu at very low energies is sort of the dimensionless strength of the interaction at around this energy scale. We see there's a logarithmic variation of the strength of coupling. And if mu is very close to the cutoff, well, lambda is just whatever the strength of the coupling is. The bare coupling is just the strength of the coupling near the cutoff, right? But there's one RG trajectory that is that's relating all of them to each other. But finally, this fact is what also lets us see from this point of view how we tame the large logarithms. So let's say that we have so let's go back to my computation of G4 of P. Now we know that we can express the answer in terms of lambda phys, right, with no reference to the cutoff. So we know what it's going to look like. It's going to be lambda phys of mu plus 3 lambda phys mu squared over 16 pi squared log p over mu plus dot dot dot. Okay? And now you see life is good because let's say that remember, I don't know what mu is. The answer is also independent of mu. Mu is arbitrary, right? I don't know what, so lambda phys is still a model parameter, right? I still don't know what any of these things are. I have to compare it to experiment to figure out what my lambda phys is. I choose a mu and I can figure out what lambda phys is, right? But now let's say we go back to that question. I wanted to know, I measure this, phi scattering at 1 GeV or something, or I measure the 4-point correlation function at all the momenta of order 1 GeV. Good. So, so then it's very simple to work out what lambda phys is. I should just put mu around 1 GeV. This term is 0 or small. And so lambda phys at 1 GeV is the thing that I measure in my experiment. Okay? Great. Now I'm done with my model. Now I want to predict what G is elsewhere. So again, if I just go a little distance, it's no problem. This formula is useful. Everything is fine. But let's say I go to P super duper far away so the log becomes large. Then am I dead? Do I have to start all over again? No, I'm not. Why not? I just solved the RGE. I know, in other words, I know that this formula is also equal to, lambda phys at some other mu prime plus 3 lambda phys at mu prime squared over 16 pi squared log p over mu prime plus dot dot dot. The answer is independent of mu prime. And so if mu prime is so far away from, if p is so far from a GeV, then clearly I should choose mu prime closer to where it is. Right? If I do that, then I've summed all these large logs by the RG. And once again, why is this working? This is working simply by the obverse of the reason that we saw that all the large logs in the Baire couplings are resummed. Okay, all the higher order logs are in fact slaves to the lower order ones, and so on. All right, but now this is said purely with reference only to what in standard books would be called renormalized perturbation theory, right? Where we don't make any reference to the Baire parameters, we just have the parameters lambda phys and this arbitrary scale mu and so on. Okay? And since we're finally at the point of the mu, again, I said it last time, but in some books, certainly a lot of the old books, you would derive things like Callan-Semantic equations and so on by just saying mu dd mu is 0, and then poof, all of a sudden you have these magical equations. And the reason was the magic was hidden from you. The magic was in the back of the books where they proved renormalizability. Okay, that's where the non-trivial step was. Whereas here, we put the magic front and center, right? The magic is actually the renormalization group front and center, and that proves renormalizability as well as all these other things that we've just been talking about. All right, so those are the two claims. We see how a lot of the physics that we're used to follows from these claims, and I'll talk about a few other things very soon besides about how to think about non-renormalizable theories and so on and so forth. But let me actually just pause for a second, see if there are any questions. Am I literally out of time?
You have 2 minutes.
Okay.
Literally 2.
Okay. Literally 2, I'm not going to do the exact renormalization group equation in 2 minutes, am I? Even though it would only take 15, but anyway. All right. Well, let me just stop. Any questions? Yes?
So sometimes we are also interested in the relevant...
Yes, we'll be talking about that. We'll absolutely be talking about that, yeah. But I can say, actually, good, thank you. This I can say. Can you
repeat the question?
Yes, sorry. So, yeah, let me just say it now. So, sometimes, here we put all this order p squared over cutoff squared, right? But what if you actually care at order p squared over cutoff squared? You have a very accurate experiment. You actually care about order p squared over cutoff squared. Maybe you don't care about order p to the fourth over cutoff to the fourth, but you care to things to order p squared over cutoff squared. So one of the beauties of this whole picture is that there's no fundamental distinction between renormalizable and non-renormalizable at all. It's just a matter of how accurate you want to be. Okay, so renormalizable is just dimensionless couplings where you don't care at all, but if you do care, you just keep going a little bit. So what is the obvious extension of claim 1? So let's say that I care about things to order p squared over cutoff squared. Sometimes I'm forced to care, but let me first make the claim. So claim has an extension, but let's say I want to keep the relevant, and let's say also lambda 6. Okay? And then I have lambda 8 and all the higher order guys. So this would have mass dimension -2, let's say. And all of these would have higher mass dimensions. Then the claim is that this is equal to g of p, where I have to slightly change what I meant by the relevant and slightly change what I meant by lambda 6, but I set lambda 8 and all the rest of them to 0. Okay, and now plus do corrections of order p to the fourth over cutoff to the fourth. So you care more, you have a few more operators. Okay? And the extent that you have to, the number of operators you keep is precisely dictated by the accuracy with which you want to know the answer. Okay? Now this is in fact practically true, because in some cases in the real world, we're forced to have even the leading interactions be irrelevant. The leading interactions for pions are irrelevant because the pions have a shift symmetry. Okay? A slightly simpler version of this is if you have a scalar field phi, just a single real scalar field phi, and the symmetry phi goes to phi plus constant. Okay? Then if I just ask what are the interactions I can have d phi squared, and then the first thing I can have is d phi to the 4 over some mass scale to the fourth with some constant plus ... Okay? So this is a theory where, for good reasons, the leading interaction is irrelevant. Okay? Now, in this theory, am I scared? It's non-renormalizable. It's a terrible theory. Can I calculate loop diagrams? You bet. In fact, in these theories, life is even slightly simpler. You see, we have these interesting beta functions for dimensionless couplings precisely because they're dimensionless. They can renormalize themselves. They can change themselves under the RG. But in this case, let's say I take this d phi to the 4 interaction and I compute this loop diagram, right? Using that d phi to the 4 interaction. Well, what am I going to get? There's 2 powers of 1 over m to the 4th, so this is 1 over m to the 8th, p to the 8th, and there's a log cutoff squared over p squared. Okay? So what I'm inducing under the RG is an even higher dimension operator. It's a dimension. It's an even higher dimension operator with 8 derivatives and not 4. Okay, now if I can have 5 minutes, Oliver, because this is an important point, but I think I can make it in 5. Okay, so
I'll let you know when it's done.
thank you. So so a very important point here is this is a non-renormalizable theory, but there's a completely reliable prediction. Okay? The reliable prediction here is in the coefficient, some number here, a, and the coefficient of p to the 8th log p squared. So you notice that p to the 8th log cutoff squared, that's just a number. So that means there's some number times p to the 8th. Some number times p to the 8th is just as if in the Lagrangian there was a term that was sitting there to begin with that looked like 8 derivatives on phi. Okay? That could just be sitting there. I have no idea what its coefficient is. I can't calculate it. I can't predict it. I need still higher energy physics to tell me what that coefficient is. But the thing with the log, I don't need. The log is a property of the low energy theory. It's not dominated by high energy physics. In Euclidean space, this is clear because of the reason we've talked about many times. You get the log by equal amounts of contributions from all scales. So it's not just dominated in the UV. It comes from everywhere. That log also has a very important Lorentzian interpretation. So when I have, even in my 5 to the 4 example, so here I had something that in Euclidean space was log cutoff squared over p squared in Euclidean space. Exactly the same thing. The Euclidean p squared is negative of a Lorentzian p squared. Okay? So in a Lorentzian theory, this would be log cutoff squared over negative s. And the claim is that this log negative s part, that's the part that's totally reliable. Now, why is that part totally reliable? Because if I think for physical s is positive. That minus sign is scary. That's why we need the I epsilon to make sense of all of this. And in fact, there is a branch cut in the s plane that begins at s equals 0 and goes to s positive. That's crucial because this amplitude, now we're not just talking about a correlation function in Euclidean space. We're talking about a scattering amplitude, right? And the imaginary part of the scattering amplitude, is given by unitarity as that cross-section where you put the intermediate particles on shell. But where do imaginary parts come from? They come from non-analytic parts of the amplitude. That's the key word to always remember. Anything that's not analytic in any quantity, here it happens to be Mandelstam invariance, momenta, but anything that's non-analytic in coupling constant, masses, Mandelstams, anything that's non-analytic in field theory is something that's coming from calculable long-distance physics. In Lorentzian signature, this is because this log, the imaginary part, which is the discontinuity across this branch cut, is there in order to correctly reproduce the ability, in order to correctly have unitarity, the fact that you can actually have this 2-to-2 process that's completely fixed by the light particle content. Okay? So the logs, that's why the logs are special. Similarly here, in this theory, I have p to the 8th log p squared, and the coefficient of p to the 8th log p squared is just the cross-section for this 2-to-2 process, where you cut these intermediate lines. Right? That's why the logs are totally calculable. Now let me give another example, and then I'll end, that also sort of emphasizes, so this is a slightly technical sounding thing, that things that are non-analytic in momentum space like this are quantities that we can, that are a property of the low energy theory, and that's why we can compute them. Let me give another example in quantum gravity. So as we drew this picture yesterday, imagine that I have I'm looking at a one-loop correction to the gravitational scattering between two particles. So using this, if I can compute this amplitude, I can go back to position space, Fourier transform, go back to position space, take the non-relativistic limit, and see an effective potential, right? Like we normally do. Well, what is this guy? Schematically, as a function of the, if I look at whatever these diagrams are, there's a normal piece that's p squared, but there's a correction that goes like 1 over m Planck squared, p to the 4th, just by units, but again, log cutoff squared over p squared. And there's some specific number here that I'll tell you what it is in a second. Okay, but once again, there's a piece of this that is not calculable. The constant piece that just goes like p to the 4th is not calculable.
It's your 5 minutes.
Yeah. That is the thing that would have been there if there was an r squared operator in the theory, right? But I can't calculate that. To know that, I have to know something about the details of the UV physics. But the piece with p to the 4th log p squared is calculable. And it's totally calculable because its imaginary part has to do with the production of the light particles that we know are there in the real world. Okay, and what I want to stress is that this business about the non-analyticity has a very intuitive understanding back in position space. Let's just see what potential I would get from this. So if I invert this propagator, so it's some number p to the 4th, and then there's a very specific number p to the 4th log p squared over m Planck squared. Okay, let's just expand this guy out. Yeah, I'm just going to finish this and that's it. There's not another topic, but yeah. No, there's not another topic. Yeah. Yes, yeah. Well, we're just finishing quantum gravity after all, so it's fine. Yeah. Right. Yeah, right. So if I just expand this out, there's a 1 over p squared. And to leading order, there's a 1 over n Planck squared. And so there's this number that I don't know, but there's a number that I do know, a log p squared. Plus dot, dot, dot. All right, now, let's from this propagator go back to position space. We just Fourier transform back. We take the non-relativistic limit to get some effective potential. We don't have to think because everything's going to happen by dimensional analysis. This gives us 1 over r, right? So what is this going to give us? This first term,